In this chapter, we focus more on our canvas and where our picture is, not just our pixels. Here are our associated media learning goals for this week to help us build our program. Here are our computer science goals for this week. We previously discussed our image as a matrix in Chapter 4. Arrays are only a row. Remember back to your math classes. Think of a picture as a graph. The height and width are your x and y, and your values fill in the matrix. Indices is a multiple of indexes. More than one index is classified as an indice. The bracket, that thing here, often represents an array, hence the listing of these three properties. 1, 2, 3. There are two variables, height and width, so we need two for loops. Here are the two for loops in action. We have them nested, so when width changes, height follows suit. Here we fill in the matrix for 0, 0. We continue to build our matrix results through the loop. Once a pixel is found, we can modify it, as you've seen in Chapter 4. Once width is found, we find height. We have now found our coordinates for this particular pixel. We continue through the program to fill in our matrix. Knowing where the pixels are helps us to edit an image. Here's how mirroring would look like with a matrix table. Mirroring is the opposite. Think of a funhouse. Mirroring can be done horizontally as well as vertically, but it may not look as good horizontally. Here is an example of mirroring not looking great when done horizontally. Similar to our prior example of copying top half to bottom half, here we do the opposite. Here is an example of how our previous code of copying the bottom to top would look. Mirroring is a common effect used in social media today, such as Snapchat. Understanding where pixels are helps produce an effective image mirroring. You might edit your code based on your image. For example, one image may look best horizontally mirrored, while most others won't. These functions allow us to find where media is stored or retrieved from. Here is example code representing media paths. Here the code for mirroring an image based on our pixel matrix is provided. Mirroring may not produce the best of images. Having an inaccurate pixel count can cause issues. Print statements always allow us to help when debugging errors in code. The opposite pixel should be the goal, but may be difficult. Understanding the number of pixels also helps debug image issues. Our additional rows are multiplied by our additional columns. As you see here, 70 additional rows, 263 additional columns to produce are 18,410. Mirroring isn't the only way we can move pixels. Modifying images in Python can use real-world possibilities too, such as collages, cropping, and scaling. Empty files can be used as a canvas to create new images on. Here, we're being given examples of the size of the canvas, 264 by 480. Our pixel pairs of X and Y always be changed together to avoid distortion. The canvas discussed here is the area where the image is stored, not our learning management system. Comments help in identifying what you're doing in your code to an outside viewer. Without our image in Canvas, we cannot edit an image. Here we begin producing our copying code. We need our loop in order to copy all of our pixels. Ending our loop instructs the computer on what to do. Think of this as an iteration. 1 plus 1 equals 2, 2 plus 1 equals 3, etc. Closing the copy function helps produce our new image. Copying the pixels helps produce the copied image. Transforming is like minor alterations for an image. An example transformation might be only copying something to a specific area. Here you notice that the image is copied to a small section of our canvas. These next 4 slides, here, the initial setup, next, and last, show us what is being done behind the scenes when copying. Adding multiple images to one area is common. This is a collage. Sometimes the code can be extensive when you think about the way it is written out in English. Again, using for loops helps us reduce repetition and make our code much smaller. The code produces the same output. Rotating may be more appropriate for files, but the sample code is here for how we do it for an image. Rotating also relies on knowing where pixels are. Again, we need to know where the pixels are. Here is code rotating an image sideways. Cropping is, however, more common with images. Try out the code on these slides. See what happens. Try this code as well. See what happens. Scaling is editing the size of an image. Often creating a large scale image will distort what your image looks like. Here is sample code for making an image smaller. Try it out. The following slides show us what is being done behind the scenes when scaling an image. We're growing the picture, we're coding, how it works again. What's going on behind the scenes is what we see here. This is how it ends up. With usual images, large scaling is not done to avoid distortion. However, there are some things we can do to address this. Here is code we can use to prevent or limit distortion created from blurring. The increased size of our pixels can distort them. This blurring code can help address that issue. Can you notice the difference between these two images? Do you notice the blurring? Which one is blurred out? Can you figure it out? Make sure to test out these programs in the Jython environment for students, even different images, to see how different inputs impact the output. And that is all for this week in addressing how to modify images in different ways.